Okay, these are some rotational kinematics problems we did in class. So I'm just going to go through them real quick and video them. And this key's posted as well in your Google site. So these are the ones where we went through the equations. So remember, here's our equations. Hopefully these will be familiar to you as we go through them. These are our version of our acceleration, time, initial, final velocity, and acceleration equations for rotational motion. So notice, theta, the angle, that was our x or y displacement. Omega is velocity. That's our angular velocity, our radians per second. And then alpha is our angular acceleration. So same equations, same relationships. Time is the same, but the other variables have been exchanged with angular quantities. Okay, so we got a bicycle wheel. We're given the radius. We're given starts from rest. So that means he's got an initial angular velocity of 0. Accelerates at a rate of 4.5 radians per second. So that's my angular acceleration. For 11 seconds, that's my time. What's his final angular velocity? So we need his final. So this is where you should note what your givens are, note what you need, and then look at your equations. Remember, with kinematic equations, there's those 5 principal variables. There's initial velocity, final velocity, acceleration, time, and displacement. And if you got 3 of those, you can always use these equations and get the other 2. And use the equation that makes the most sense, that's the easiest to use. In this case, I've got initial velocity, acceleration, and time. I want final, so I'm going to use this first one because it's the cleanest. It's got 3 of the things that I need, and it gives me the 4th if I put those in there. So I don't have any information on displacement with this particular problem, so I don't want to use the other 2. So I'm going to use that equation. I'm going to put in my values for acceleration and for time, and I get 49.5 radians per second. The next one is similar. It's like the same bicycle wheel. Same scenario, starts from rest, angular acceleration, time. Now we want displacement, okay? And so I'm going to use this equation instead in this case because I want displacement. I know it started from rest, so that term goes away. I know angular acceleration, I know time, and so I'm going to solve for the displacement. And that's how many radians it went through for that 11 seconds. So that's like, equivalent to an X or a Y. How many meters did the bike travel? This is the angular version of that. How many radians did it travel through? Okay, different wheel this time. So, all right, so now we've got a 50 centimeter diameter wheel. It accelerates from, so remember from and to are clue words, from 5 revolutions per second to 7 revolutions per second in 8 seconds. What is its angular acceleration? So we're given our initial and final angular velocity. That's our from initial to final. We're given time. We want alpha. We're going to use this equation because we've got 3 of these things. We want the 4th. With this one, there's a little complication, which is that you can't use revolutions per second. So there are several ways, to measure displacement in a for a rotating object. There's revolutions, there's degrees, and then we prefer radians in physics. So if you're in one of these other two, you have to convert. It's like if you were in centimeters or kilometers and you want to convert to meters because you need to stay in meters. Okay. So if we're going to convert these from revolutions per second, we know that in one revolution there is 2 pi radians because that's your full revolution one time around the circle. So I do 5 times 2 pi. That gives me my initial angular velocity in radians per second. Same with my final velocity, 7 times 2 pi. And then I can put those numbers in the equation. So there's just an additional step there in terms of converting. And remember, like for a full circle, 2 pi radians equals 1 revolution, and that also equals 360 degrees. So keeping those things in mind just in case you had to convert. Okay, another wheel. Let's see. So this one I changed up the last one just a little bit to use a different equation. So same wheel accelerates from 5 revolutions per second. We already had figured out that that was 31.4 radians per second. We're given its angular acceleration in time, and we want displacement. So I'm going to use this equation. This is my initial angular velocity, so I'll multiply that by time plus 1/2 times 2 for my acceleration times 8 squared for my time, and I end up with 315.2 radians. This one, a lot of times this term goes away if you're starting from rest. Here we weren't. We were starting our scenario where our wheel was at 5 revolutions per second or 31.4 and then accelerated. So all right, now we got a wheel that's slowing. It has an initial angular velocity of 24, but it's slowing at a rate of 3 radians per second. So I gave that a minus sign because it's slowing. By the time it stops, it will have turned through how many radians? So that tells me I need displacement. And it's going to come to a stop in this scenario. So that's my final. So here's one where we get to use this third equation because I don't have any information on time at all. But I've got my velocities, my acceleration, and I want displacement, which is in this equation. So I'm going to use this equation. I'm going to fill in values. I have 0 for my final velocity. I have 24 for my initial. I have to square that. Plus 2 times minus 3. And you see how the minus helps here because this, when I subtract it from both sides, it's got a minus sign. Acceleration, I gave a minus sign because it's slowing down, but then those cancel. So I end up with 96 radians as my displacement it went through before it stopped. Okay, let's see if I can get through these last couple. So we've got a fidget spinner moving at an initial angular velocity of 84.5 radians per second, and it takes 80 seconds to stop. Like it's one of those where, it's eventually slowing down due to friction, comes to a stop. At what rate did it slow down? So that's where I'm looking for acceleration. So I've got an initial angular velocity, a time, a final velocity of 0, and then I'm going to use this version of the equation. Just plot values in there. And I end up with a minus for the acceleration because it's slowing down. Okay, and then last one. I can get all these in one video. A record starts from rest and turns through 22.5 radians in 10 seconds. At what rate is the record spinning? So starts from rest, initial velocity 0, displacement 22.5 radians in 10 seconds. We want acceleration. So here I've got time and I've got displacement and I've got an initial velocity And so I'm going to solve for acceleration. That's what I want. So I put in my displacement. It starts from rest, so that one goes away. 10 is my time. I have to square that, and I end up solving it and get 0.45 radians per second per second. So that's a quick review on rotational kinematic equations.